Okay, good afternoon. Questions? Run, homework or design assignment? Remind me which one is 3?
That's the one about the bit adder.
Okay.
Can we use logic sims like adders that?
No. I think that's the problem where I have said you can only use half adder and full adder.
Oh, okay.
Yeah,
So we can't use
you
logic
cannot. Yeah, so, well, if you look at logisim's full adder and half adder, it only works for single bits. Okay.
Okay.
Yeah. Logisim has something called an adder, which you are not allowed to use. Okay. The intent out there, so look, you are always in these problems, and this holds true in an exam setting also. When I say create something, it doesn't mean create a design. It doesn't mean you have to create a flat design. You can always make a part of the design, give it a name, and then reuse it in a different part. The way you kind of do it in Logisim with subcircuits, that's perfectly legitimate. So, for example, if you think you need a n-bit adder, create it using the full adder, and that we have shown in the class. Okay. So, yeah, use hierarchy. In fact, I mean, it's encouraged. And also, I see questions like, can I use splitters and all? Of course you can, because they're just wires. They just help make drawing easier. Okay. Likewise, there's a question about, can I use n-bit AND gate? Sure you can. It's just a compact way of drawing things, right? I mean, an n-bit AND gate as opposed to a k input AND gate, right? K input AND gate ANDs k things. And n input AND gate is basically saying, if I have an if I have an n-bit 2 input AND gate, that's really saying I have n AND gates of 2 input each, which are just stacked in parallel. Okay, as long as you count the cost correctly, it's nothing but a compact way of drawing. I often use them in slide. Textbook uses it. It's pretty common. Logisim allows it. So anything which is merely about making the drawing more compact is legitimate. So hopefully that answers your question. Okay.
So when we use reverse wire splitters to
Sure.
combine wires, like how do you want us to tell you which order the wires are combined?
Just, like how in Logisim it just puts a little bit index code, you can always just use that. Okay. So just remember one thing, your homeworks are graded by a reader who is someone who took the course last year. So the point I'm trying to make is that you have to make things easy for him to understand. Questions like, can I leave a messy Logisim thing? Not really, because it's very unlikely that he would have the time to decipher. The department pays him 10 minutes per homework, so it's not a whole lot. So I guess the thing I'm trying to say is put yourself in the shoes of someone grading your work, okay, and sort of present things in a manner which is easy to understand, because otherwise your grade will take a hit, and there's only so much we can kind of accommodate by way of regrade requests. So just help us out. Then in any case, it's a good idea to kind of make things clearer. Things like hierarchy and splitter actually help in that front. Okay, they make your design more readable. Other questions? I see a lot of trouble over problem number 5, the one about 2's complement and things like that. I sent a Piazza mail just like maybe 20 minutes ago, but just wanted to sort of mention that I think many of you are kind of missing some obvious indicators. Okay, so like you don't, while certainly if you knew the bits, the problem becomes trivial, but then I wouldn't have offered a problem with 7-8 points for those 2 parts. The reason is I want you to think about how bits relate to numeric value. Okay, so that's point number 1. Point number 2 is numeric value of a number is its innate property. It's independent of whether I choose to represent that number as bits or digits in base 10 or hexadecimal digits in base 16 or whatever, base 23 or anything else that I may choose. So now it so happens that when we refer to numeric value of a number, we usually think and talk in terms of base 10, but that's just cultural or societal thing, right? I mean, you could imagine a society where people spoke binary, and it would have come very natural to them to have some other language, right, expressing binary numbers. But so even though when we see 100, we say it is 8. We don't call it 1000 in base 2. So that's the second point. Third point, and what that was the intent behind the mail was, let's say I give you some number x, and I say, okay, what is the value represented by its lowest bit? Well, the value represented by its lowest bit, either a 0 or a 1, indicates whether it is an even number or odd number. Now, certainly one way of looking at it is, hey, tell me what are the bits behind x, and I will say the answer is b0. But I don't want that. I want just something in terms of x. So I'm really looking for the remainder divided by 2, right? So x %2, or whatever, x modulo 2, that gives me the least significant bit without having any access to. What about the number represented by the lower 2 bits? That's modulo 4, right? So, so this thing is going to be equal to x0, number represented by x0. X mod 4 is the number represented by x1, x0, and so on and so forth, right? So I've already solved the unsigned part for you if you just think a little bit more, okay? Similar relationship you can now figure out for 2's complement. That requires more thinking, but the main point of this exercise is that I don't need the individual bits, and don't search for loopholes in the English language there, in the sense that it kind of defeats the purpose of the question if you find some tricky way of saying, okay, bit 0 is this, bit 1 is this, bit 2 is this, because you can, someone looking at it immediately say, hey, I can get all the bits now, because I can one by one do these mods and kind of start getting the kth bit and then use the sigma formula. It kind of defeats the purpose of the thing. So think in terms of just given x, what's the natural way I can figure out if the top few bits were locked off, whatever is left over. So approach it from that perspective. I see kind of some of you, okay, or perhaps many of you, because most of you are choosing to post anonymously, you try to find holes in the English language of the question, and that's not a good strategy. It's not going to work later in life also. Try to go with the spirit behind the question as opposed to seeing whether there is a gotcha and which can let you get away with. So when you start asking, can I use these operators, or like is not gate a gate, things like that, I think you're wasting time. You know what the answer is going to be. Yes, not gate is a gate. You have to count it, or what operators are arithmetic or not. It's kind of obvious, okay? So things like that. So again, the spirit of the question out here is, I don't want you to make use of individual values of bits. Extracting them and doing a sigma over them, nah, that defeats the purpose behind the question. So that's what I would say. So unsigned I have solved essentially through this thing. I hopefully can, just a trivial extrapolation from that. Signed one is trickier. If you recall, when we do signed number and express it in terms of bits, then the lower bits, all other than the signed bit, every other bit gets the same weight as in the unsigned case. The most significant bit gets a weight of minus 2 to the power w minus 1 as opposed to 2 to the power w minus 1. So you have to think about what the implications are. It's certainly okay that you can extract somehow the value of that one bit and see what the effect might be, or play some other game. But any solution which attempts to just extract all the bits and does a summation over it is not complying with the intent of this question. Let's see what else I wanted to say. Okay, finite state machine questions. So there's some question about, one of the questions is about transitions. The transition is being referred to there is a transition on the data input line, and specifically what it is saying is the state machine is observing the input at every clock tick. Okay, if it's a mode machine, then basically at every clock tick, whatever is the input value at that time, that gets used to define the next state. So when we are talking about transition, what we are really saying is that the input was 1 and then became 0. So in one clock tick, I saw it as a 1. The next clock tick, I saw it as 0. So that's what happened. Data input has nothing to do with the clock signal. So while we do talk about that flip-flops update themselves when they see a transition in the clock line, you should not think in terms of feeding the data line into the clock input of the flip-flop. So your design would look like the D flip-flops in your design are all sharing a common clock. And that common clock is coming from a clock source. It's a periodic signal. And nothing from your data should ever mix with the clock. Okay? You should not have any gates between the source of the clock and the clock inputs of the flip-flop. Okay? So you should not attempt to say, I will AND the clock with this data input or things like that. That is, as I alluded to, if once you get a lot of experience and all, there are ways you can use it, but you have to be super careful. Generally speaking, if you many textbooks basically say that among the sins of digital design is getting your clocks. So just don't do it. So so anything that you wish to do in terms of these, like trying to see whether the input went from 0 to 1, 1 to 0, something happened, that should all fall out of your next state and output logic. Okay, the clocks you should not be messing with. So that's kind of the other statement I wanted to make. Let's see what other things came up. Yeah, so the encoder example, which is actually a relative. So firstly, anytime some input is invalid, then that's don't care. Okay, so in this example, the little encoder really can only see two types of valid inputs, all zeros or a single one. Anything else is invalid, not just for this little encoder, but it's invalid for whatever bigger encoder we are trying to make of it. So it's invalid. Now, having said that, I often have also said, once something is don't care, is there a intelligent way you can now pick out of the choices, and that is where other considerations may come into play. But in this example, and generally speaking, it's just fine to put XX onto the table there. And then, of course, when you implement it, you have to make some choice, whatever maybe leads to the simplest design. So that bit about don't care. For some reason, every time we have had a question on don't care, the same question comes up: can we use don't care? Yes, you can, and in fact, you are expected to or almost required to, because I want to see that you are able to realize that that particular condition is a don't care, and therefore there is a design flexibility there. Let's see, so question 1. Question 2, I don't think anything significant came up there. 3 is the decoder question, where you are given 2 to 4 and 3 to 8 decoder, and then you have to make a 7 to 128 decoder. I think that's the question. So the thing to realize is that I have 7 bits to decode, and I could obviously create a 7 to 128 decoder just using the gates, but the question prohibits it. It requires you to use two decoders. So the basic structure of making bigger decoder is that I decode groups of bits and then combine the result. So for example, I can take 2 3 to 8 decoders. That will cover 6 bits. I have a 1 bit remaining, but for 1 bit, all I need is an inverter to decode it into 1 to 2. And then I can combine the results using AND gate. So one solution would look like 2 3 to 8 decoders in a single bit. But that may not be the lowest cost. What other solutions are possible? Ignoring the cost for the moment. What other different ways I can combine these 2 to 4 and 3 to 8 decoders to create a 7 to 8 decoder? Sorry, 7 to 128 decoder.
2 to 4 bit.
Okay, so 2 2 to 4 and 1 3 to 8, that covers all the 7 bits. Good. What else? Three 2 to 4 in a single by itself, that's another one. And I think that pretty much covers the space, okay, because you have to use 2 decoders. And then you can, even without working through the circuit, you can do a back of the envelope calculation as to what the count is going to look like. I had a typo in the formula, so make sure that you work around that. And then one design stands out. One of the observations you'll probably see is that the 3 to 8 decoder is really, really expensive, so that's probably going to affect the choice. So question, so that's pretty much the way to approach that question. And yes, you have to count the cost of a NOT gate for sure. Okay, I don't know. Yeah.
Yeah, so 128 3-input AND gate. The cost is 228 times 4, right?
Correct. Yeah. Yeah, I mean, I had the cost structure earlier, and in words I said the correct thing, but the formula was missing, the k plus 1. So thanks for whoever was kind enough to point it out. Anything else? Yes.
How would you draw a splitter like?
You can kind of mimic what Logician does. Okay. And as you might notice, at least from the first homework, I don't draw by hand in the solutions I use drawing tools. So, but in an exam setting, yeah, have the wire coming in, have it fork out, put the index numbers on the forks. Yeah. Okay, so if no other questions, so the slide set that I covered last time, we kind of went over synchronous logic and kind of covered various points. So one thing being that the mathematical framework in which we think about it is that of finite state machines. And finite state machines have several equivalent representations. One is, of course, a circuit which has flip-flops and combinational logic. Another is the truth table, where the inputs are the current state and whatever input signals are coming from the outside world, and the output are the output going to the external world as well as the next state. So that's another representation. And the third representation is the state diagram, the state transition diagram, where you have nodes representing the states and edges representing the transitions. And depending upon whether your system is mealy or more, the outputs may either go into the state or on the edges. So and I showed various kind of drawing conventions and all. I will post FISM on Piazza and give you some guidance on how to use it, because in the homework after the midterm, we'll be using that as a drawing aid, as well as generating the Verilog out of that. So we saw these equivalent things. We talked about the state transition, state assignment problem. And the main point is that the states of the system are really our internal choice. So given starting with the English language description, we usually draw the state diagram, most of us at least. That's the easiest way to think about the problem. And I'll have a bunch of states. But what bit patterns correspond to those states is really our choice. The external world doesn't care about it. Other than, like I said last time, it's typical to make the start state to be the one which is all zeros, so that I can just send a reset signal and make sure that the circuit starts in the initial state. So that led to a couple of strategies that we saw last time. One was one-hot coding, and the other was sort of fully encoded. And the one-hot coding had the advantage that by looking at the FSM, you could kind of draw the circuit just visually because it followed a very nice pattern. Whereas the fully encoded one leads to a more complicated kind of thing. One of the homework problem, I think it's the very last one, asks you to write the equations. That's really nothing but the equations corresponding to that truth table. So in the problem, in the homework, there is a 3-bit of state, there is 2 bits of external world output, and there's 1 bit of input coming in. So what you really have are 5 equations, 3 for the 3 bits of next state, and 2 for the output going to the outside world. So 5 equations, because there are 5 outputs, and they each depend upon as many as 4 inputs, so 3 bits of current state and the 1 input coming from the outside world. The equations actually turn out to be very simple once you try it out, so nothing terribly complicated there. And we saw sort of several examples last time working through this. Let's see what other points I wanted to make. Okay, so and then the implementation strategy, the implementation pathway is plain English description, make the finite state machine graph, looking at it, then you make the truth table, and then implement that using by hand or Logisim or whatever that might be. And in some cases, you can even bypass the truth table. If you use one-hot coding, you can straight away jump from state diagram to the circuit. Okay? But if the problem asks you to show the truth table, then you have to show it. If I ask you to write the equations, you have to write it. So before I close this module, one other thing I wanted to cover is this concept that there are a whole bunch of other types of flip-flops that are encountered. And just wanted to show that there is nothing magical about them. They just are all derivatives of the D flip-flop. So let's do that briefly. Okay. So there are the D flip-flop, which we saw thus far, and which is what Logisim has. It basically works has a following property, right? That and it basically says that at the clock tick, if D equal to Z, so whatever is D goes to Q, okay, at the clock tick. So if D is 0, Q becomes 0. If D is 1, Q becomes 1. So that's what the D flip-flop does. So its truth table basically, in essence, basically says that so this happens at the clock tick, that at the clock tick we examine the 0, we put the 0 in there, examine the 1, put the 1 there. Okay, T flip-flop has a different behavior. So T flip-flop is represented as this. Its input is called T, output is called Q, and of course again it has clock. Its logic is that at the clock edge it puts Q gets the value. So the idea is if T is 0, Q retains the value. If T is 1, Q toggles. So we basically can write it as the following. So I'm basically saying, in a programming language style, I'm basically saying if T is equal to 1, then make output to be Q bar. Whatever is the current value of Q, flip it. And if T is 0, then retain the current value. Okay, so what would this look like? If, let's say, I have clock coming like this, and let's say T was 1, and let's say Q was initially 0. And let's say T was 1 permanently. So T is high. So what will happen is at this clock tick, Q will flip because T is 1, so we do Q bar. So Q will flip, then it will remain stable. At the next clock tick, Q will flip again because T is again 1, and so on and so forth. So every alternate clock tick, I'm flipping the output. This is when T is constant. If constant 1. If T was 0, Q would have remained 0. What do you think is happening out here? If Q is flipping in alternate bits, I'm basically generating a signal which is also periodic but has half the frequency, right? Because period has become twice. So a T flip-flop with T tied to 1 looks basically like a clock divider. It's dividing the clock frequency by 2. Okay, so if I look at this guy's truth table for the T flip-flop, it looks like the following. So I have separated out a Q. So the left column is the current value of Q. the next column is t, and then what's the next value of q out here. So if t is 0, the q remains unchanged. So this row and this row would be just that, and the row where t is 1, I will get this guy. Okay, so q next is given in terms of q like this, and then looking at this, you can just say, hey, this is like our standard sequential logic where I think of q as the state, t is the external world input, and I'm generating the next state. Well, the next state, if you look at it out here, it is high when q is 0, t is 1, or q is 1, t is 0. So this in turn basically can be implemented as, hopefully it may be obvious, but nevertheless, so this says q next so if t is high, q toggles. If t is low, q doesn't toggle. So I have an XOR gate in front of d flip-flop, and that's my t flip-flop. So t flip-flop is nothing but sort of an expansion. It's something that you can build using a d flip-flop. But since the t functionality is often very useful, so we often end up having that available as a module itself. So we saw d, we saw t. There are two other flip-flops. There is one called JK, and the way it works is so if you look at the definition of JK, it has two inputs now. So as opposed to D and T, which have a single input, J and K have two inputs. 0, 0, 0, 1, 1, 0, and 1, 1 being the four possibilities. If J and K are both 0, Q remains unchanged. If both are 1, Q toggles. If K is 1, it resets. If J is 1, it sets. Okay, so again, look, so let's so I'm just going to write it here. J, K, Q, and Q next. Okay. So I have 8 possibilities now. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so looking at this, firstly we know that if J is 0 and K is 0, then Q next is the same as Q. So J is 0, Q is 0 are the first two rows, so Q next is 0 and 1. If J is 1 and K is 1, then Q next is the negation of Q. So the last two rows are 1 and 0 because I'm just flipping the Q. Okay. Then for the other cases, if K is 1, then we reset. And if J is 1, we set. So this is a truth table for the JK flip-flop. And JK flip-flop is nothing but a sequential circuit exhibiting this behavior. And looking at this, you can hopefully figure out what the equation is going to look like for Q next, and put that logic in front of J and K so put that logic in front of a D, and so essentially you can implement. This is what I'm saying, that you have D, Q, you will have some logic out here which is going to take J, sorry, it's going to take J, K, and it is going to take Q. And it's going to be getting the next Q out here, and you can figure out what that logic would be. So JK flip-flop, SR flip-flop, T flip-flops, these are just specialized sequential circuits which happen to have be quite useful. Could you make a D flip-flop out of JK flip-flop? So I just showed you out here how using a D flip-flop I can make a JK. My question is, could you make a D flip-flop using JK flip-flops? Yeah.
If you fed D into J and not D into K?
Yeah. So if you feed D into J and not D into K, then if D is high, I'll be feeding the pattern 1, 0. If D is low, I'll be feeding the pattern 0, 1, and then I will get the requisite behavior. So you can go either way. So in many cases, you may be given JK flip-flop as a sole flip-flop, and then you may be asked to implement a sequential circuit. So one way you can do it is what you suggested, which is I can first make a D flip-flop and then use my rest of my circuitry, rest of my approach. Or alternatively, I can maybe find out a way of directly working with JK. Likewise, you can create D flip-flop using other type of things. I mean, basically, you can go back and forth. That's the main point. So there exists these other flip-flops. I think Logisim does not have them, but in real life libraries, you do find them. Being able to handle it is something that is useful. Okay. So let's. Any questions, firstly? Okay. So the next topic that. So next topic I'm moving on to is to look at, to see how that can we do everything with finite state machine, or is it better to think about some other type of sequential logic also? But before I do that, there's a couple of other things I wanted to say was normally in this course we have not touched anything to do with real hardware. This course has been all theoretical. One thing I'm planning to do is to actually have you guys, if you so choose to, work with real hardware so you can see how sort of some of this stuff can map to a thing. So the plan is the following, that if you recall, the fourth design assignment is the optional design assignment, and the way it works is if you choose to do it, then you get graded on it. If you choose not to do it, then whatever is the weight for the fourth design assignment essentially gets added to that of the final exam. So your final carries more weight. So the plan is the following. I'm acquiring a bunch of little FPGA boards, which FPGA is a type of chip to which you can map circuits. So think of it like instead of the circuit being simulated in Logisim, the circuit now gets sent to this FPGA. This board has a bunch of LEDs, so you can create circuits which sort of work with those LEDs. It has a clock, and it has a bunch of I/O pins. I'm also going to give you a little keyboard. Okay, it's like a telephone keypad type thing. So it has the 10 digits and a star key and a hash key. And you would have to implement a combinational lock, in effect, one which can give in a number and some pattern can lock and unlock. And except that instead of a real lock, it's your LEDs. So the LEDs will indicate whether the lock is locked or unlocked. Okay, so that's kind of the plan. But again, you can entirely choose to skip it. The way it will work is we'll hand out the hardware. If you don't return the hardware back to me before the finals, then you don't get graded. So that's the only leverage I have. If you drop the class, I can't control it. But I think it would be a fun assignment. Now, the way you would do it is the following. We are, unfortunately, commercial tools to work with FPGAs are quite a bit of a pain, partly because of licensing reasons and all. So, and they don't work on Macs, which many of you have. So what we have done is we have figured out an entirely open source design process. The only bad part is it works under Linux. So we'll have a Linux server. You submit a file, it will give you the design, and then you can download it to the FPGA. So that's how it's going to work. We hope, so the lecture on May 17th is going to be done by a PhD student of mine, together with Salma, who's one of the TAs, and they will walk you through the design process as well as introduce you to Verilog, which is the design language. Now, Verilog is a complicated language, so we'll just show you a subset of it sufficient for you to be able to do something like this. Okay, basically we'll show how you can write a state machine, and we'll show how you can write a combination logic, and you just follow that pattern. Verilog can do a whole bunch of other complicated stuff, which you'll probably see in some later class if you choose to. So that's kind of the plan. So May 17th lecture is going to be that one. Since it's going to be a lot of demos and stuff like that, in that we'll show how to work with it. If you decide to skip the lecture, unfortunately, we cannot really record it, okay, because a lot of the action would be not on the screen, but would also be in the physical board. So do plan to attend that one, but that's a new thing we are introducing this time around. Again, if you choose not to do the final that design assignment for, that's perfectly fine too. The only other thing is, since it's a new thing we are trying out, there'll probably be growing pains, okay? We'll discover along the way, so we'll have to cope with it as we go along. Alternatively, I mean, if you decide not to do it, then your only other exposure to that kind of design in our undergraduate curriculum is if you choose to take 116L, if you are an EE student, or CS 151B or 152B, one of the lab classes, 2 unit, I think it's 152A. It's the same, it's a cross-listed course where you work with FPGA boards. It's required of all CS students, it's required of EE students who historically followed the computer engineering pathway, but if you're a regular EE student, you will not be taking it, so in which case, so this can be a fun thing for you to do. Okay, so back to the lecture. What we are now going to talk about are a type of sequential systems where we start thinking of it not in terms of just a state machine, which is moving from state to state, but we start thinking of in a slightly different manner. So what I would like to say is the following. The concept of state is just one of memory. And if you think about your software programs and all, there are 2 types of state that we deal with. Okay, so when you write a program, there are variables where we store state, and we do arithmetic of them. We say x is equal to y plus z, right? So y and z are memories, x is a memory. We say take these 2 memories and add them and put them in x. These are all registers, and they're part of the state too. Now you may say, what is happening out here? Am I doing some sort of state transition? Yeah, you are. If you think of x, y, and z as being your state vector, then before you did the addition, you were in some state where x had some value, y had some value, z had some value. After I do the operation, I move to a different state where y and z have the same value as before, and x has the summation of the 2. So these arithmetic operations done on registers or other operations done on variables are also state transitions, but we never think of them that way. On the other hand, things like if x less than 0, do some operation, and if it's greater than equal to 0, do some other operation. That kind of smacks of state transitions. We are looking at some value and then kind of making a transition. So the point I wanted to make was that not every state necessarily lends itself to thinking in terms of jumping from state to state. Part of the problem is that our variables have lots of bits. So take a variable in your regular computation. So machines nowadays are 64-bit. So if you have a variable x it has 64 bits. Right there, you have 2 to the power 64 states. There is no way you can ever draw a state diagram for it. And by the time you think of a more complicated system with a bunch of state variables, you add their bits, you're probably going to have few hundred, maybe many thousands of bits. 2 to the power of that is really the number of states. You cannot draw it as a state diagram. So we need some other way of thinking about sequential machines where there are all these states. On the other hand, our programs also have this other kind of state, which is as the sequence of instructions we are following. Which branch did I take? Where am I in the for loop? Okay, that kind of state is easily captured using what we saw in the previous lecture. We can think of it as states in a state machine, and I'm jumping from state to state. That, those of you who have done CS33, that's your program counter. It's basically saying where in the code I am. So very succinctly then, there are these 2 types of states. States on which we do arithmetic and logic operations, and they have many bits, and they intuitively at least are not lending to the formalism we have. There are just too many bits. And then there is state, which is like describing the flow of the program. Where am I? How am I jumping, branching, things like that. That works well with the state diagram that we talked about. So this lecture, we are going to look at that other type of thing where we have variables and we are somehow manipulating them. We cannot conceivably express them as a state diagram, so we need some other way of dealing with them. So that's what this lecture is going to be about. So that's chapter 16. So dealing with lots of states. Let's start with consider a counter. Okay. So what does a counter do? It basically has some memory, and at every tick it increments the memory, right? So I can think of that counter as going through. So if it's a 5-bit counter, it will have 32 states. So I can say it's in state 0, 1, 2, 3 through 31, and every clock tick it just moves from one state to the next state numerically higher. And if there is a reset signal, I go back to the 0th state. So we express this thing as a counter. Logisim has a counter module. You can implement this thing by having by trying out the state diagram and then working out the logic. So I can basically have something like the on the state table, given the current state on the leftmost column, I can figure out the next state and then work out the circuit. In this case, it would be some sort of an adder with a reset messing with it. Okay, so I can certainly follow the approach that we saw in the previous lecture. Now let's say I tell you I need a 64-bit counter, which our machines have. That's how they maintain time. This approach falls apart, right? I mean, 64 means 2 to the power 64, which is roughly 10 to the power 60. That's huge, okay? So how do we deal with those kind? If I start dealing with these large counters and large number of bits, other such things, what can we do about it? So yeah, so the example is 32-bit states, so same problem holds true. So what that leads to is a way of thinking about sequential systems, not in terms of they jumping from states to states, but in terms of what is called as data paths. So usually in our computers then, or in our digital systems, there are 2 types of sequential logic: the state machines and data paths. So what are data paths? Data paths are entities in which there are registers which hold data, and we have operations which manipulate that data. Okay, kind of like a program. So I may have a register called A, a register called B. I can say on a clock tick, take A, take B, add them, put them back into A. I can define operations on the data path, much like we do in a program. So in case of a counter, I can say something like the following. I can say, imagine there is a register called state or count. Okay, I'm calling it state. And I am now allowed to express operations on it as if I'm writing a program. So I can simply say next state is equal to if reset then 0, otherwise state plus 1. So those of you who are familiar with programming, I'm sure you have seen this before. This is an operation which basically goes that the stuff before the question mark is a condition. So it says if condition is true, or in our case, if it is a high bit, then the value of this whole expression is the one before the colon, namely 0. And if the condition is false, then it's the next one. So if reset is high, then next state will get the value 0. If reset is low, the next state will get the value state plus 1. So now we begin to think of how the state is changing as kind of like a program, okay, kind of like a operations that would be typical of a software thing. So this is an example of a very simple data path. This data path clearly has an adder, it has a multiplexer, and it's then doing stuff to this register which we call as the state. So what this is allowing us to do is that we are no longer thinking of the state as bunch of nodes in a graph among which we are jumping, although we could, and nor are we thinking of it in terms of a truth table. We are just thinking in terms of some expressions in a pseudocode like fashion. So yeah, okay. So I could then write this thing. What this lends itself to do is to kind of write a state table which is kind of symbolic in nature. So I basically say if the current state is A, then the next state is either A plus 1 or 0. And now, given that expression, I can draw my circuit relatively straightforward. So I have a single, I have a register called state, whose next value I'm calculating. So that's my state register. Okay. And then basically what I'm saying is that the next value of the state is equal to state plus 1 or 0. There are two choices. So this question colon operator is like a multiplexer. So that's what we have, the multiplexer. If reset is 1, then I get the 0. So that goes through. If reset is 0, then here what we will have is count plus 1. So count plus 1 is what will feed throughout here. And it's an n-bit circuit. So so that's this thing is clearly sequential. It has a state register, but I'm not thinking of it as a state diagram with nodes and all. I'm thinking of it as doing some operation on every clock tick. So this core idea we build up now to create more complicated things. So this is a simple counter. So one thing which you would notice out is that there are two types of variables that we are seeing in this expression. There is count, which is like data, it is n bits, and there is reset, which is a single bit signal, right? So this is the state variable out here is kind of like data, and this reset is kind of like control. It's a single bit signal, it is affecting how we are operating on it. So usually you will have a mix of these two kind of variables. There will be some variables which are multi-bit variables, they are kind of like data, they are data, you are manipulating them and all. And there would be some other variables which are really acting as a control, they are affecting what operation we are doing. And that's very typical of the way, again, in your programming classes you would have seen. We say things like, if some condition, do something, so that's where we are dealing with flow of the data. And then our regular variables where we hold the data are kind of like our the variable called state out here. So what that leads to is the following, that our data paths are again kind of are basically a good old form of sequential circuit where I have a state register, I have a next state logic, and I have an output logic, and except that I'm thinking about these logic in terms of these expressions, and our data our state is where our data resides. And I'm showing it as a single register, but it could be a whole bunch of variables, X, Y, Z, whole bunch of things which I'm manipulating on every clock tick. So these things are now described as functions. So let's take another example. Let's say I want to create a more complicated counter now. So I want to create specifically what is called as an up-down load counter. What this counter can do is it can express three behaviors. It can count up, it can count down, or it can be loaded with a new value. So the idea is that I'll have some sort of a control signal, and depending upon what that control signal says, the counter on a clock tick will either count up or count down or look at some input and load a new value into it. So in particular, this counter, if you see, has a count signal which is n bits. It has an input signal which is n bits. And then it has a reset signal, and the signal is called up, down, and load. These are 1-bit signals. So these are control signals. And of course, we have clock. So what we seek to do is, on a clock tick, depending upon what reset, up, down, and load are saying, I will express some different behavior. So let's see how that might work out. So we may have something like the following. Okay, it may say, if reset, next state is 0. That's another way of saying that if reset, then counter becomes 0. I'm forcing the counter to 0. The next statement says, if not reset and up, then next state is state plus 1. I'm incrementing it. Third condition is, if reset is false and it is down, then next state is state minus 1. Okay. And now, I guess my pseudocode here is not very good, so I should have said else out here, because otherwise what if both up and down are high? If not reset and it is load, then next state is in. So now whatever is at in, I load it into the counter. And otherwise, if reset is low, up is low, down is low, load is low, then the counter freezes. Okay, so that's the freeze part. Now, idea behind this thing is, for this thing to work correctly, at most one of the 4 inputs should be high and the other should be 0. So that's kind of the logic out there. What about the output function? The output function is simple. It just says count is equal to state. Okay, that's all I'm outputting. So now I have taken a more complicated thing, but again, hopefully you would see that the pattern out here kind of looks like the way we do manipulate data in a program. Okay, so we are kind of writing it like that. We have these if then else clauses, stuff like that. Looking at this, anytime you have if then else, then you start thinking of multiplexers, because that's how we steer the flow of logic in different direction. We have seen examples like when we did the median in the first homework, where you use multiplexers. So we've seen examples like that where we looked at the data and then kind of select different options. This is precisely what is going on out here. So I can create a table version, but the table version is far more complicated. I can create a symbolic table where I do it in terms of what is happening to the states, somewhat better still, but I can literally go from this program to this circuit by just staring at the program and then mapping, following some pattern. Okay, if then else, map to multiplexers, operations like plus and all correspond to adders, addition and negation. So what I can do out here is, the way we implement this thing is, we imagine there is a multiplexer. So go back out here. See, next state has 1, 2, 3, 4, 5 possibilities. It can take the value 0. It can take the value current plus 1, current minus 1. It can take the value coming on in, and it can take the value state. So I kind of need a 5-to-1 multiplexer, which is kind of ugly. So we'll say, okay, how about we do a compromise? Let's do a 4-to-1 multiplexer. I combine two of these cases. So we know add and subtract are kind of very similar. So I'm going to put them into a single option. So that's the strategy we take. We say, okay, let's imagine I have a 4-to-1 multiplexer and I have 4 options. I have the option of feeding count as is. So that's first option. I have the option of feeding in. That's the second option. I have the option of feeding 0. That's the third option. And I have the option of feeding count +1 or -1 as the final option. And then which option I select has to be decided by the control signal. And those control signals are going to depend upon these 4 signals. So I'll need some sort of a combinational logic to let me decide which path to select. And likewise, whether I'm doing a plus or a minus also has to depend upon what is happening. So in particular, I'm going to do, if down is high, then I'm going to do a negative. So here I'm going to feed a 1. If you recall, if I take an adder and I feed a 1 to its carry in, then it acts as a 2's complement. If I take an adder and also have XOR in front, so we had designed this add sub circuit where there was an input called sub, and if we made it high, it did a subtraction. So that's what we have sitting out here. So all these control signals help us generate the real signals that we need out here, inputs to the multiplexer and input to our plus-minus module. So our task then boils down to making this CL. So now if you look at it out here in this multiplexer, it says that I would steer a 0 when multiplexer input says 0. So our multiplexer here is one hot multiplexer. So I'll have to say that it gets a 0 when, under what condition? When reset is high. So when reset is high, multiplexer should get a 0. So presumably in this circuit, reset will feed to the select line for 0. What about 1? We get a 1, we select input 1 when either up is high or down is high. So there will be an OR gate. We select in when it's a load. So for input 2, load would feed in there. And finally, if everything is low, then it is the other input. So we can kind of create a combination logic to make this magic happen. So our job now, in our original sort of circuits, we were designing the entire combinational logic. Here, by parceling out this multiplexer and adder and all, we have now a simpler combinational logic task remaining, just the controls for these multiplexers and arithmetic units, and that usually you can just stare at the logic and kind of write down the equations. Typically tends to be straightforward. So that's the schematic for the up, down, left counter. But again, we never thought of it in terms of its state diagrams because it would have been just insanely complicated. Thinking of it like a program and then mapping it to these arithmetic multiplexer registers with a little bit of combinational logic sitting outside. So this part is usually called the control logic. So this is taking our control signals and then massaging them a little bit, and then it is controlling the arithmetic stuff, controlling the multiplexers, and then of course I have my state register. So we're going to look at more examples after we take a 5-minute break. But what you have seen now are a couple of data paths, a simple counter and this kind of a more complicated counter with some glue logic sort of helping us out. So let's take a 5-minute break and we'll continue.
Hey. 5e, how thorough of a description are you looking for? For 5e, how thorough of like a description are you looking for how like to make a solution?
I have to look at the expression for that, but is it a valid expression syntactically in the sense of what I'm now using? I don't know whether its value adds up to what you're looking for or not.
Okay, but like, how do we describe?
Yeah, you can write something.
Okay, so you're just mainly going to be looking to see whether that's correct.
Yeah.
Okay, thank you.
It looks very complicated though, so might be probably correct. I don't know, but looks complicated. Okay, question?
Yeah, it's a review lecture on Thursday.
Huh?
It's a review lecture on Thursday.
So send me questions for it to be effective. And the TAs will again do another review during the discussion sections. Okay, so let's look at another module in the same vein. So something again which Datapath kind of an approach will do much more easily than kind of trying to draw the state diagram. So we're going to look at a timer, not too dissimilar than timers we encounter in real life, kind of something where you start, stop, it counts, it freezes. You have apps like that on your phone. Okay, so there are many computing systems, actually pretty much anything reasonable would have some way of doing these kind of timers as well. So this is a simplified version of that. So I have a module, I want to design a module which takes a reset signal, it takes a load signal, it outputs a done signal, and the way it works is the following, that if I if I assert the reset signal, the timer should reset to 0. If I assert the load signal, then some value from the outside world is loaded into the timer. Okay, so it's kind of like setting the timer to, like if I want to have it count down for 5 minutes, I'm loading 5 minutes into it. There is a done signal, so the counter starts counting down. When it reaches 0, it raises the done signal. So again, kind of like the chime out of the timer on your microwave oven timer, for example. Okay, and then otherwise the timer decrements. So every clock tick it decrements. So kind of intuitively the usage operation would be a load a value by asserting load and presenting the right value, and then I will let it count down, and it will keep decrementing from that. So let's see how we might approach this thing. So the done. Let's think about what are the possibilities. So one is I want to make the next state to be 0. Another is I would like to make the next state to be whatever is on the in bits. And finally, the third case is that I would like to make the state to be state minus 1. Okay, so that's the decrementing part. And what about the done signal? The done signal is basically saying that I have reached all zeros, which basically is another way of saying is that all the bits are 0. So that is what this is saying. So it's basically saying it's not the case that any of the bit is 1. Okay, so that's the right hand side out here. Okay, the left hand side is basically the 3 cases. So it says if it is reset or it is not load and the done signal has been asserted, so the counter has counted down. Okay, then I stay put there. Once I have reached the state 0, I want the counter to freeze at that stage. So the way we are doing it is we are making use of our own output signal done, and we are saying if it is either reset or alternatively it's not load and we have counted down all the way through, the next state is 0. So that's the first clause. The second clause is if it is not reset and load is true, then next state is in, and then final clause is otherwise we count down. Okay, so that's the final clause. So there are 3 cases, and again this smacks of a multiplexer, but again sounds like a decrementer sitting in front of it, so something which does a -1, and the 3 cases are going to be feed a 0 or feed in or feed the output of the decrementer, and then the control inputs of the multiplexers have to be controlled by these 3 conditions. Okay, so we can create something like this. We can have a 3-to-1 multiplexer, which basically is a tripled multiplexer. We just don't need the 4th case. And what you see out here is 0 is being fed in is being fed in, or count -1 is being fed in. And then again, I will have some logic out here, which will take reset, load, and done, and then generate the control signals for the multiplexer. And then finally, I'll have something which checks equality with 0 to create the done signal. So again, once I have that program-like description of Datapath, coming up with this is playing with multiplexers and some operation. So again, what you see out here is the same pattern we see in the previous examples. There is stuff happening out here which is happening on n bits, and then stuff happening out here which are 1-bit controls. or 1 or very few bits usually. Okay, so that n bit of data is kind of like a variable. If we are manipulating the count, we are saying make the variable 0, make the variable +1, stuff like that, the typical things we do in a program. And then the stuff out here, this control logic, or which I've called as a select logic, is the one which is where the control flow is happening. It's controlling the multiplexer or multiplexers, if there are more than one, to make things work out. So this style of making hardware is kind of like, instead of compiling your software to work with machine code, you're compiling your software to work with multiplexers and arithmetic operators and this kind of logic. So it's sort of, there are tools which do this thing. They can take your C code and all and literally map them to these kind of data path structures automatically. They can extract things. They can look at what things are n bits, what things are single bits. They can extract a data path and they can extract this select logic for you. They have gone under the names of things like silicon compiler, hardware compiler, behavioral synthesis tools, all sort of names. But they exist. They cost a lot of money, but they can do pretty cool stuff. You can feed C to them. So there are versions of Verilog which are meant for this kind of high-level thing. So there's something called system Verilog. But a very common thing is to actually just use C. So you write your hardware description in C. It goes under the name of system C. And then you, instead of running it on a regular compiler, you run it on a different tool, and it kind of figures out all these things. They even kind of do things like, oh, what about we have 2 adders instead of 1 adder? What would be the impact? They kind of do all sort of optimization also. So there are pretty powerful tools available now which can kind of take reasonably complicated C code and map it into data paths like this. Let's take another example. Shift registers. So what's a shift register? Shift register basically shifts the bits. These are the less than and greater than operations in the programming languages. So how might this work out? So so the logic that we want is the following, that if it is reset, then out is sent to 0. Otherwise, what we are doing is one by one, we want to shift out the bits. So I have a multi-bit register in which I have loaded a value. And then on every clock tick, I want to make one of its bit come out. Okay, so let's say I loaded 1010. Then what I want the output to have is on one clock tick, I should see 0 if I'm starting from the right. Next clock tick 1, then a 0, then a 1. So one by one, I'm going to shift the bits out. So what it looks like is the following. If reset, then next state is 0. Otherwise, next state is, and this is let's see. So next state is 3-bit. Actually, hang on a sec. Did I misspoke? Okay, so in this case, actually, I'm shifting things in. So my apologies. So this is what we are trying to do. I have a register. I loaded some value into it, 0, 1, 0, 1, 0, let's say. So that's the initial value. And then what I'm going to do is every clock tick, I'm going to shift the contents of this thing left. So this will shift left, so it will become 1, 0, 1, 0. And in this space, what I'll do is I'll feed in whatever was on an input called SIN. So there is a 1-bit input. I'm going to examine it, and I'm going to put its value into that register. Okay, so I'm feeding in, I'm shifting left, and I'm feeding in whatever is the value of SIN is at the time. So what this thing is saying is the following. Next state, which is an n-bit number, I want to make it such that its upper bits are what used to be bits 0 through n minus 2, because n minus 1 1th bit, the most significant bit, I have discarded. So the upper n, so this is up now the upper bits of new state. So this is in effect saying the following: I'm taking these lower bits and I'm mapping them to this guy. So this is what this guy corresponds to. It's taking the lower bits other than the most significant one and then making it the upper n minus 1 bits. And the final bit is Sn, which is out here. So the least significant bit becomes Sn. So I'm basically describing this shifting operation that is happening. What does shifting mean in terms of circuits? What kind of gate would I need? For going from SIN and current state to the next state, what kind of gates would I need to make this happen? So again, I have a state register. It's giving me bits 0 through n minus 1. I have to load into the next values from the D input. I have to load things such that the upper n minus 1 bits are what used to be the lower n minus 1 bits, and the least significant bit is what SN is, what SIN is. SIN is a 1-bit input. So my question is, what kind of gate or logic can cause such a shift? Yeah.
Technically, depending on how tricky you want to be, if it's a multiplier or technically no, nothing, because you can just disarm.
Yeah, it's just wiring.
Yeah.
So no, not a multiplier. It's just wiring, right? All I have to do is what is shown out here. So I just shift the wires. What used to be n minus 1 is, sorry, what used to be n minus 2 is now n minus 1. What used to be n minus 2 is now, what used to be n minus 2 becomes n minus 1. What used to be n minus 3 becomes n minus 2, and so on and so forth. And then Sn feeds into the 0th location. Okay, so it's just wiring in Logic. You're just shifting the indices by 1. No logic required. So shift operation is pretty trivial, right? Okay, it's just rewiring things out. So this shift register is just a multiplexer, which I load 0 if it's reset. Otherwise, I shift and feed in the SIN. Any questions on this? Is anyone not convinced that this is just wiring up things right? No gates needed.
Yeah, I mean, is it like in real life? So how the shift is actually like physical component?
Nothing. It's just wires.
What do you mean? How can you like in a device?
I can always take. So, do you agree that this state has n bits, right? Okay, and this input of the multiplexer out here has n bits, right? And I want this input to be shifted in the manner that I had described, right? Okay, so what I can do is I can take the n, so the bits out here go from 0, well, they go from n minus 1 down to 0, right? I can physically say, okay, the n minus 1th bit goes nowhere. The n minus 2th bit here goes to n minus 1th bit here. I can connect that by a wire. I can take the n minus 3th bit here and connect it to n minus 2th bit out here. So if I were to draw it, let's say this was my state thing, and let's call this guy X. This is X. All I'm doing is I'm wiring this guy so that it goes here. I'm wiring this guy so that it goes here. I'm wiring this guy so that it goes here. I'm wiring this guy so that it goes here. And I'm wiring SN to this guy. So it's just a matter of connecting the right set of things.
But like in an actual computer, no wires are moving, right?
Huh?
Like in an actual computer, you shift left or shift right. No.
No, hang on a sec. We are not. This is hardware we are making, right?
Oh, okay.
Right. So imagine in Logisim, you're just wiring things up. In a chip, it would be metal wires connecting one gate to another gate. In a FPGA, it would be some connection. Now, in a computer, when you do less than operator, it's presumably doing using some logic which does something like this, right? I mean, arithmetic left shift versus logical left shift with feeding some bits into the LSB location. It would probably be using some hardware like this. But we are in the world of hardware right now, right? And at the hardware level, a shift is nothing but taking the content of the register and feeding them back into the register with a skew of 1. Okay. You can also create, what if I wanted to shift by a different amount? What if I wanted to shift by 2? Well, then you just skew it by 2. Okay. If I wanted a shifter which can shift by an arbitrary amount, then what I can do is I can have a big multiplexer and then feed different versions of the shift to the different inputs of the multiplexer and then select the right one. There is a type of module which is called barrel shifter, and the way it works is the following. Its intuition is the following. Let's say I want to shift by an arbitrary amount. Okay, so let's say I tell you I want a module where I can shift by 0, shift by 1, shift by 2, all the way through shift by 31. Okay, so one approach you can say is, okay, I'm going to create 32 different shifters and then select one of them. But the other option you can think of is the following. Let's say I want to shift by 3. Then I can think of it as shift by 2 shift by 1 followed by shift by 2. If I want to shift by 9, that is shift by 1 followed by shift by 8. If I want to shift by 27, then it is shift by 16, shift by 8, and shift by 2, and shift by 1. So by just having shifts which are powers of 2, I can concatenate them and create an arbitrary amount of shift. So a barrel shifter is a specialized module which does that. Most computers have it because programming languages like to have this option, less than n, okay, where n could be arbitrary. So shifters are a valuable part, but they are pretty easy to implement. Okay. This kind of shift register actually has another very important use. Your computers have serial ports. Now the reason they are called serial ports is because data comes over wire serially, 1 bit at a time. But in your computer, inside your computer, we want to then treat it as a single variable, n-bit variable. So what happens in the serial ports, there's a hardware in the serial port called UR, but one of the things it does is it takes bits coming in serially and assembles them into an n-bit word, which is what this guy is doing. It's taking stuff coming in Sn and one by one it feeds it. Then, so it's a serial to parallel converter is also what this is doing. Okay, so useful for serial to parallel conversion. And of course, you can imagine there would be something in the reverse direction also. Serial, your regular serial port, your USB, these are all examples of serial things. Data goes over the wire 1 bit at a time. But inside the computer, it has to be parallel. So circuits like these help go back and forth. Okay. Let's look at, how are we doing with time? Okay. Let's look at something even more complicated variant of this. Okay. So now what we have is a bidirectional shift register. So what we want to do now is on reset it goes to 0. I can now tell it to shift left or shift right. If I tell it to shift left, it is like what we had previously, which is it shifts left and the least significant bit is filled with the SIN. If I shift right, it does the other way around. It shifts right and the most significant bit is filled in with SN. Okay, so this is what happens out here. And then finally, there is a load so that I can load a value into this guy. Okay. So, and otherwise out is unchanged. So again, what I can do is, as usual, we kind of again think of it like a program. We kind of write these different cases. So our cases are now set to 0, leave it unchanged, set it to in, shift left, shift right. So there are 5 cases, which is what I have listed out there. And then output is whatever the state is. So that's what we're kind of just outputting. Again, you would see that I'm using this funky syntax out here. What this guy is saying is that the next state is assembled such that its upper n minus 2 bits are made using what used to be the lower n minus 2 bits. And Sn is the new LSB. And when I'm doing the right shift, then Sn is the new MSB. And the lower n minus 2 bits are what used to be the upper n minus 2 bits. Okay, so just sort of a syntax like that. There's nothing, I mean, this is pseudocode, so there's nothing, I'm not following any particular language. But if you were to be using, let's say, Verilog or one of these hardware description languages, they do provide syntax for this kind of stuff. Okay, so implementing this, as you can imagine, I need a multiplexer with 5 options. I create all those options. Okay, so there's an option for feeding count state itself, feeding in. So that's this case, feeding in. I have option for shifting right and shifting left, but these shift right and shift left are just those rewiring. Okay, just recall from the previous case. And then finally feed 0. And then I will have some select logic. This is some simple gate, set of gates which take these signals and generate the necessary signals for the multiplexer so that the right thing happens. So for example, for the case of 0, that means load is, sorry, that means none of them are high. So the select input corresponding to option 0 would be when all of these things are 0. So it would be a NOR gate. Okay, and likewise. So again, the logic would look relatively straightforward. So again, emphasis, these shift left by 1 and shift right by 1 are just rewiring of things. Okay, it's just how you draw the wires there. So what we have seen thus far then is that for certain kind of logic, certain kind of operations, it's preferable for us to think in terms of n-bit variables on which I'm doing some operations, as if we are writing code. And then they end up mapping into registers, multiplexers, some n-bit operations, and we steer, we make the right thing happen by having some control signals. So we control the multiplexer and we may control some of the operations like add sub, whether it does an addition or subtraction. So real systems, as in most digital systems, tend to have this kind of behavior. They'll have a part which you can easily express using the state diagram which we saw in the previous lecture. And then they will have a part which you have to express using this kind of a data path because it is dealing with n-bit quantities and they have massive amounts of state in them. So real systems then tend to usually have these two halves. They will have a state machine which is handling the control part, which is saying what's happening, what state is the system in, and things like that. And that we design using what we saw in the previous two lectures. And then they will have this data path part, which we design using what we saw thus far. And the two talk to each other. The control signals, which helps make the data path do the right thing, come from the FSM. Okay, and then the output of the data path goes back to the state machine. It tells the state machine, hey, there is an overflow, or I'm done, or those kind of things. So the two talk to each other. So this control FSM is what we design using this we design using state diagram and this we design using sort of code, if you may, kind of looks pseudocode type stuff, the operations. Okay. So inside the data path, you would have things like multiplexers, adders, registers, and stuff like that. And inside the control FSM, you would again have registers, the state registers for the control FSM, and you'll again have combinational logic, but it would be kind of, it will be more random. It won't have this kind of nice n-bit structure to it. Then what you see is that some inputs go to the control FSM, and some inputs go to the data path. Some may go to both. And likewise, control FSM outputs some signals, the data path outputs some signals. And the two talk to each other. There will be some status signals going from data path to the controller, telling it what is happening in the data path. Is there an overflow? Did the number underflow? That something get done? Things like that. And controller is going to be sending signals to the data path saying, at that clock tick, what should be the setting for a multiplexer? Should the adder be doing, add sub be doing addition or subtraction? Things like that. So basically sending signals which help configure the data path. So at every clock tick, this thing happens that the control FSM tells the data path what to do, and the data path gives information back about what it did. Okay, was there an overflow? What happened? And then based upon that, the control FSM will jump to a different state and again decide. So like for example, you have things like, if an overflow happened, then do something else. Okay, so you can have that kind of logic happening out there. So if you think in terms of your programs, then the if then else, for loops, those kind of things usually get mapped to something happening in the state machine. Whereas operations like add two variables, multiply them, put them into a different variable, all those things are happening in the data path. So that's how the two kind of end up interacting. And this partitioning is kind of, there's no hard and fast rule. It's certainly possible that a design could be done all in data path. It's certainly possible that a design could be done all as a FSM. It's certainly possible that you can divide the two, and maybe there are different ways of dividing them. Okay, what is data and what is control is oftentimes not very clear cut, and in that case, you may come up with different solutions. But so this kind of partitioning is something to keep in mind, that some things are better done as a data path unambiguously. If I'm adding two 64-bit numbers, you are not, and creating another 64-bit number, you are not going to do it as a state diagram. But certain things may be ambiguous, and given a design, you will kind of have to decide that. So data path computes its next state, kind of as if it is manipulating program variables, and it does so using multiplexers and n-bit operations which are things like shifters, adders, counters, those kind of things. Whereas control FSM computes its next state using the next state table kind of structure that we saw previously. And control FSM sends commands to the data path, and the data path sends back the status. So that's what we saw out here, command, status, and that's what we see out here. And then finally, inputs coming from the outside, again, fall into these two categories. So just to, for example, if I'm getting an input from a sensor which is telling me the current temperature reading, and I'm going to be processing that temperature reading, maybe take averages, multiply it and all, it's clearly data. Okay, it's some n-bit number. On the other hand, if I'm getting a signal from the outside, from the sensor saying, hey, the data is ready, it's a 1-bit signal, then it's clearly a control signal. So again, when you look at the specification of your system and look at it, some things, I mean, they'll fall into one of these two categories. Okay, it could be a control type stuff or it could be a data type stuff. The usual giveaway is if it's something which is n-bit and you are going to do that n-bit type processing, it's data. If it is 1 or 2-bit signal which is telling you some status or something like that, or something got done, then it's control. And depending upon that, your partitioning will happen. A lot of this comes with experience. intuition, just how good a designer you are. And again, there is no right or wrong answer. You can certainly do a lot of things one way or the other way. Also, you can certainly, if you so wish, put everything in a data path. There are ways in which you could do things entirely in a data path for certain kind of designs. So no right or wrong answer on this partitioning. So this controller is a state machine. So one thing I would emphasize is that now I really have two finite state systems. Okay, each one of these individually is a finite state system. This data path is also finite state. It has some state registers which have a finite number of bits. So it also has finite states. It's just that we don't like to think of it in terms of a state transition diagram. We think of it as arithmetic and logic operations being done. So, but that's just how we think of it. So control FSM basically has two types of inputs. It is getting inputs from the outside world and it is getting inputs from the data path. And it takes those things in as inputs to the state machine out here, and then it does the state transition and it generates two types of outputs. It generates the output going out and it generates commands going to the data path. Okay, so this is a state machine. And then the data path is kind of the same thing. It is taking data input from the outside world and it is taking control commands from the control FSM. And then it is updating its state. It is sending data out to the outside world. This might be, for example, processed sensor data, for example. And it is also sending some status signals back to the control FSM. So what we have now are a system where I have two simpler sequential systems and they're interacting with each other. Okay, one handling the control part, one handling the data processing part, and that's my overall system. This is a very common way of designing digital systems, as I mentioned earlier, that generally speaking you will have these two parts. In fact, generally speaking, you will have on your chip or in your system, you will have multiple such things. So you may have multiple such groupings of data path controller, and they kind of talk with each other. You can think of them as multiple threads or computers kind of interacting with each other. So let's see. I think I'm going to stop out here. So next time, which would be really after the midterm, we are going to use these insights into a more complicated system design exercise. Okay. So again, Thursday I've reserved for just A, answering your questions, and B, kind of going through some problems.